Welcome back to Chapter 3. Today we're going to talk about measures of variation. So measures of center is what we covered in the last class, and that tells us basically where the middle of our data set is. Today we're going to be talking about how spread out the data is, and we're going to look at different measures for that. Okay, so this is a very important topic as we look at statistics, and there's three different ways that we'll measure variation. Range is probably the one that's most familiar with you. You've probably been calculating range of data sets for many years, even dating back to elementary school. So hopefully that'll be familiar to you. And then standard deviation and variance are really the measures of variation that's used most in more formal statistics classes. So we want to be able to calculate these, but our calculators will do most of this for us. So while we're going to look at a couple of calculations, it's not going to be anything long and drawn out. And most of the time, I'm going to expect that you just get it from your calculator. What's really important, though, as we go forward, is to be able to interpret and understand these particular statistics, the standard deviation and the variance. Okay, as far as rounding rules for variation, it's actually the same rounding rule that we looked at in the last section, and that is that you want to carry your answer one more decimal place than is present in the original data set. So if you have two decimal places showing in your data set and you have to give your some type of variation, whether it's standard deviation or variance, you would carry that to three decimal places. So it's one more than whatever's present in your data set. Okay, we're going to look at three different measures of variation. The first we said was range, and range is simply the maximum minus the minimum. And then we'll look at standard deviation and variance, which kind of go hand in hand, and you'll see why those two go together. Okay, so the range is of a set of data values is the difference between the maximum and the minimum data value. So pretty simple calculation for us there. Okay, one reason we don't really look at range very much, and we talked about before with measures of center, which ones were resistant to outliers and which ones were not. The range is not very resistant to outliers, so it's very sensitive to extreme values. And that's simply because if you think about the way range is calculated, with it being the maximum minus the minimum, then those outliers are going to be your maximum and minimum, and therefore range is going to be significantly impacted by any type of outlier that you're using for the calculation. Okay, so here's an example. If we're finding the range of these Verizon data speeds, you can see that we have the data here. If it's a large data set, my recommendation would be to enter it in your calculator and sort the data so that, and then do the one variable stats that we talked about last time, and it'll give you your maximum and your minimum on that listing. And from there, you can easily identify what your maximum and minimum are to do the calculation. For this small data set, we can clearly see that the 55.6 is our largest value and the 14.1 is the smallest. So if we subtract those, we get our range. Okay, moving on to standard deviation. So the standard deviation of a set of sample values is denoted by the letter S. Okay, so if it's coming from the sample, that's important. If it's coming from the sample, it's going to be using an S, and that's a measure of how much the data values deviate away from the mean. Or in other words, how far are they spread away from the mean. So as far as other notation, S we said was for the sample standard deviation, and sigma is for the population standard deviation. Here you can basically visualize what I'm talking about, hopefully with standard deviation. You can see that with a smaller standard deviation, your values are going to be clustered closer to the center of the data. But as your standard deviation gets larger, your data values will be spread out more. So the blue would have a smaller standard deviation, the red would have a slightly larger, and then the yellow, the data values are spread way out, and so they therefore would have the largest standard deviation. The green one would have a different measure of center. So you can see where the yellow, the red, and the blue are all centered at the same value, and they just have different standard deviations. If we're looking at the green actually has a different measure of center as well because it's shifted away from the center that these others are around. Okay, a couple of formulas for finding standard deviation. We have this formula here, which is more of a conceptual formula. We said that the standard deviation was a measure of how much the data values deviate from the mean. So here we're doing a calculation that involves taking each data value, subtracting the mean from it. So you're looking at how far it is from the mean, squaring it, adding those all up, dividing by n minus 1, and taking the square root. So you can see that's a pretty involved calculation. We are going to go through this with a small sample data set and work with it. There is a shortcut formula for doing this, and this doesn't look a lot shorter, but it really can be if you're trying to work with a larger data set. Okay, a couple things to remember. The value of a standard deviation is never going to be negative, and it would only be 0 if every single one of your data values are exactly the same and they don't deviate at all from the mean. Then that would be a case where your standard deviation is 0. Otherwise, it's going to be some positive value, and the larger your S is, the more variation you have in your data set. Okay, standard deviation can increase dramatically with outliers, and the units of your standard deviation is the same as the units of your data set, so you're not going to see any difference there. And our sample standard deviation S is actually considered to be a biased estimator of the population standard deviation, and we'll talk a lot more about that in chapter 6, but just know that S is considered a biased estimator. Okay, if we look at this data set here, we have these 5 same data values, actually, yeah, 5 data values. We're going to use this conceptual formula here first, and then we're going to look at calculating this using the shortcut formula. Okay, if we look at this and our formula, we've got to find our x bar. So if you want to put it in your calculator, you can find x bar, or you can actually add all of these up and divide by 5. If you add them all up, it's going to be 153.7 divided by 5 is going to give us 30.74. So that's the mean. So according to this formula, what we've got to do is we've got to take each one of our data values and subtract the mean from it. And then we're going to add all of them up because that's what this summation means. It means add them all up. So we'll take each data value, subtract the mean, and then add them all up. Okay, so following our formula, we've taken each data value and we've subtracted the mean from it that we found here. Here's our 5 data values. Each one of those, we subtracted the mean from it. And looking at this, we actually need to go in and square each one of these. So we're going to square the difference between the data value and the mean. And then this tells me that we're going to add them all up, which I've got the addition signs to do that. So when I do that and do all the calculations, I'm going to get 1083.052 for that part of it. Okay, now we've got to divide by n minus 1 and take the square root. So S is going to be the square root of this number that we just found here. And we're going to divide it by n minus 1. Well, n is our sample size. So in this problem, n was 5. We had 5 data values. So n minus 1 is going to be 4. And then when I do the calculation for that, I'm going to find that I get 16.45. I'm rounding this to 2 decimal places because my data set have 1 decimal place shown. So I need to go 1 more than that, and so it'll be 16.45. Okay, let's take a look at the same problem with the same data set, except this time we're going to use this shortcut formula for the standard deviation. What I've done over here is I've put this data set in for L1, and I've run the one variable stats from the calculator. So this is what you'd see on that screen there. And I wanted you to notice there's a couple things that will really help us in doing this calculation. One is the sum of the x squareds. So if I didn't have this information, I'd go through and square each one of my data values and add them up and put that here. But since I have that, I'm actually going to use that. So n, we already said from the previous example, was 4 because it was, 5. So n is 5. The sum of the x squareds is going to be this 5807.79. And then we're going to subtract from that the sum of the x's, so 153.7. We're going to square that, and then we're going to divide that by n, which was 5, and n minus 1, which was 4. So when you put this in your calculator, be careful about order of operations, but you should end up getting that same 16.45 for your answer. Okay. And so this is just a little bit nicer screen showing this. Okay, so on your calculator, I've gone through these examples with a very small data set just so you can appreciate these two formulas. But in reality, we really do not want to be using them very much, if at all. So on your calculator, on this one variable stats menu, you can see you'll see an S sub x and a sigma sub x. Your S sub x is the one for the sample, and your sigma sub x is the one for the population. I will tell you in this class, I cannot think of a single time that we use the sigma sub x. So you're always going to be using this S sub x when you're asked to give standard deviation. So if you're asked to give standard deviation, my expectation of you is that you enter the data in your calculator, you run the one variable stats, and you write your answer down for the standard deviation. You're not going to be calculating using these formulas. I did want you to understand where they came from and what everything represented, but you're going to be from here forward just doing your calculator to get this answer. That's why it's important that you round it correctly, because really all you're doing is using your calculator to get that value. Okay, a couple other things to mention here when we talk about variation. One is the range rule of thumb for understanding standard deviation. And it's just like it says, it's a rule of thumb. It's not anything concrete and exact. It's a guide for interpreting the standard deviation. Basically what it says is, since the vast majority, and we're saying here as many as 95% of your sample values lie within 2 standard deviations of the mean, then we can use that as a guide for understanding this standard deviation. So we say that values are significantly low if you look at the mean and you subtract two standard deviations, and if it's below that, then it's going to be significantly low. If it's above the mean plus 2 standard deviations, then it's significantly high, and anything in between these two is not considered significant statistically. So looking at this, you've got, here's your mean. If you add 2 standard deviations to it, then those are significantly high values. If you subtract 2 standard deviations, then those are significantly low. And here, anything but in between is not really considered significant. Okay, so we have a couple of examples here. The first example is males have pulse rates with a mean of 67.3 beats per minute and a standard deviation of 10.3 beats per minute. Is 45 a significantly low number of beats per minute for a male? Is 95 considered significantly high? So we've got a couple questions here. You really need to get in the habit of being able to interpret this and write your symbols down. So here we're talking about the mean, and presumably this is of all males because there's no indication of a sample. So that's going to be mu. So mu is going to be 67.3 beats per minute. And the standard deviation is going to be sigma, because again, that's referring to all males, so therefore it's a population. And that's going to be 10.3 beats per minute. Okay, so if we want to find out, is 45 a significantly low number of beats per minute for a male, we need to figure out what the mean minus 2 standard deviations is. So that's going to be 67.3 minus 2 times 10.3. And that value, okay, that value is 46.7. So when I look at this, my mean we said was 67.3. 2 standard deviations below is going to be 46.7. If I wanted to figure out the high side here, I would do 67.3 plus 2 times 10.3, and that would give me 87.9. So anything between 46.7 and 87.9 is considered not significant. Anything above 87.9 or below 46.7 is significant. So in this, our question, is 45 a significantly low number for a male? Since 45 is down here, it would be considered significantly low. If you look up here at 95, 95 is above this, so it would be considered significantly high. So that's what you want to use for your comparison purposes with this. Here's an example. I would suggest that you pause it and try this problem and then check your answers. Okay, our mean on this one is 12.19 and the standard deviation is 0.11. So if I do 12.19, I like to just combine them together and do plus or minus 0.11. So if I do the addition part to that, I get 12.41. And if I do the subtraction part, I get 11.97. So anything between 11.97 and 12.41 is considered not significant. Anything above 12.41 is significantly high, and anything below 11.97 is significantly low. So 11.9, that one would be below 11.97, so it would be considered significantly low. 12.3 actually is in the interval, so it would not be significantly high or low. Okay, we have another range rule of thumb. This one's for estimating a value of the standard deviation. So with our range rule of thumb, we use that S is approximately equal to the range divided by 4. So that's just a rough, as it says, guide or rule of thumb for being able to estimate the standard deviation. I want you to think about this. Why do we actually need a range rule of thumb for estimating a value for the standard deviation? If I were to ask you the question, what is the mean height of Wingate students? We may not know the exact answer for that, but you would be able to at least give me some estimate, maybe 6'10", 6'11", 7 foot, something like that might be the highest, and then the lowest might be like 4'7", and on the low side, so the mean therefore might be like 5'10", 5'9", something of that nature. So we have some idea of how to find the mean height of the Wingate students. But when I go to ask what is the standard deviation, this should say of standard deviation of the height of Wingate students. We really don't know where to start. Like you don't know if that would be, 2 inches, 10 inches, 20 inches, 80 inches. We don't really know until we have some estimate for that, and that's where this range rule of thumb can be helpful. So we said that it was going to be the range divided by 4. So let's just say that we think the range we know is the maximum minus the minimum. So let's just say we think that the tallest person at Wingate is 6'11". That would be 83 inches if you did the conversion. And let's say maybe we think the shortest person is 4'7". Okay, so that person, if we converted that, would be 55 inches. And so I divide that by 4. So we see that this is going to be approximately 7 inches for our standard deviation. So while we know enough about the mean to be able to give some kind of estimate for it, we generally don't know enough about the standard deviation to be able to give an estimate. So if you're asked to give an estimate for the standard deviation, this range rule of thumb can be helpful. It's just simply your maximum minus your minimum divided by 4. Okay, just a comment here. We really don't work with populations that much just because populations are usually large enough that we're going to pull a sample and work with that. But if by some chance we were working with a population, then your standard deviation you would take and divide it by this capital N. And capital N is the population sample, the population size. All right, variance. We've been talking about standard deviation. Variance follows very quickly from standard deviation. Variance is the set of a set of values is a measure of variation equal to the square of the standard deviation. So if you have the standard deviation, you just need to square it, and then you have the variance. So our sample variance is going to be S squared, and our population variance is going to be, and this is sigma, it's going to be sigma squared. Okay, so here's a couple examples. If the variance is 100 inches square, we want to find the standard deviation. So if I'm going from variance to standard deviation, I actually just take the square root of that. So the square root of 100 is going to be 10, and the square root of inches squared is going to be just inches. If I have 15 liters squared, if I take the square root of that, then that's going to be the square root of 15 liters, and you could put your decimal answer in here depending on your directions. But if I turn around and go the opposite direction, if I have the standard deviation and I'm asked to find the variance, then instead of taking the square root, I'm going to square it. So 4 squared would be 16. And if this were inches, then I'm going to also square that. And so it's going to be 16 inches squared. So your variance should be a squared unit, and your standard deviation is not going to be a squared unit. So here, 8.5 pounds. If we square that, then 8.5 squared is 72.25, and that would be pounds squared. Okay, so this is just kind of summarizing our notation that you really need and have to know this. S is for sample standard deviation, S squared is sample variance, sigma is population standard deviation, and sigma squared is population variance. One way to remember is generally our population ones are going to have Greek symbols. Okay, so that's a little bit helpful. Okay, here's the same example that we worked with before, and we calculated our measures of center. So if you still have those handy, then you can pull those out, and if you don't, then you might want to recalculate them. You want to enter Jefferson Valley for L1 and Providence for L2, and then go through and find your measures of center, which are mean, median, mode, and mid-range, and then find your measures of variation, which are range, standard deviation, and variance. Then I want you to see if you can answer these questions about what can you determine about the similarities and differences, and are any of the wait times significantly high or low? So I would like for you to pause this and work on this problem, and then unpause it to check your work. Okay, so these are the measures of center that you should have gotten. Again, those are the same as last time. So just as a reminder, these were exactly the same for the measures of center. If we take a look at our measures of variation, for the standard deviation, this is the number that the calculator gives you. And when you report your answer on this particular problem, because our data set So our data set on this one had 1 decimal place given. So when we do our calculations, we want to give our answers to 2 decimal places. One thing I wanted to make very clear is that you want to consider this entire value. Obviously, rounding it for standard deviation isn't a big deal, but if you take this answer and square it, you're not going to get the correct answer. You need to make sure that you take this whole long unrounded answer, square that, and then you can get the variance. So the variance needs to be the square of the unrounded standard deviation. Don't take the rounded value for that. So you can see that when we look at this, Jefferson Valley has much smaller measures of variation than does Providence. Providence has a lot more variation, so the data values are spread out more. We had the other question of which values are significantly high or significantly low. So if we look back at these measures of center, when we look at Jefferson Valley, we would do our mean plus or minus 2 times our standard deviation, and our standard deviation on that one was 0.48. So we're going to get a range on that one of 6.19 to 8.11. For Providence, we're going to have 7.15 plus 2 times our standard deviation there is 1.82. So we're going to end up with 3.51 to 10.79. Okay, so consider these intervals here, and if you look back at your data set, on that particular data set, Providence had the highest value, and that was 10, but even 10 is still within this range. that we would expect using the range rule of thumb with this. Our smallest value was 4.2, and so it still fits in here. And everything at Jefferson Valley also fits within the range within these values here. So actually, that none of the values in either of the data sets would be considered significantly high or significantly low. Okay, a few important properties about variance. Variance is, with this, we talked about that the units of the variance are going to be the square of the units of the original data values. The variance can be affected greatly by outliers. The value of the variance is never negative. And then finally, sample variance S squared is an unbiased estimator, which that sounds a little bit unusual since S is a biased estimator, but we will take a more in-depth look at that in chapter 6. Okay, so looking at the empirical rule for data with a bell-shaped distribution, this is again a general guideline that tells us about what percentage of data values we expect to be within a certain number of standard deviations. So this is called the empirical rule. It is important that your data set is approximately bell-shaped. So if you're told that it's normally distributed or approximately normally distributed or it's bell-shaped, that's sufficient. If you have like a uniform distribution or we have a highly skewed distribution, then these values are not going to hold for that. So it is important to have this bell-shaped distribution. What the empirical rule says is that about 68% of all values fall within one standard deviation of the mean. About 95% fall within two standard deviations of the mean, and 99.7% fall within three standard deviations of the mean. So again, these are just guidelines. They're not set in stone, but they are guidelines for a particular distribution. And this is just a visual kind of showing. You can break it apart. You've got your mean here in the middle, and you've got your 68% that's going to fall within one standard deviation. If you go out two standard deviations, then about 95% of the values fall in here. And if we go three standard deviations out, you're going to capture 99.7%. So really, you're just going to have a 0.3% of your values that are not going to be within three standard deviations on a bell-shaped curve. Okay, here's an example of using the empirical rule. It says IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ scores are between 70 and 130? Okay, if we start out with our mean of 100 and our standard deviation of 15, if I do 100 plus one standard deviation, that's going to take me to 115. And if I do that plus another standard deviation, then that's going to take me to 130. So that's going to be my mean plus two standard deviations. If I look at going in the opposite direction, 100 minus 15 would be 85. And then if I subtract another 15 from that, that's going to put me at 70. So that's the mean minus two standard deviations. And going back to the empirical rule, if we're two standard deviations away from the mean, then that tells me that 95% of the data values are going to be between these two values here. So you have to just kind of work your way and to get to these values and see how many standard deviations you are away from the mean. Okay, here's another example, and I'm going to give you a minute to try this, and then we'll take a look at your answers. Okay, if you look at part A, for part A, if we take our mean, which is 98.20 degrees Fahrenheit, and our standard deviation is 0.62 degrees Fahrenheit, if we add those and look at what one standard deviation takes us to, one standard deviation is actually going to take us to 98.82 degrees. So that means this is one standard deviation above the mean. And if I look at subtracting that, then that's going to take me to 97.58. And so this is one standard deviation below the mean. So since these values are within one standard deviation of the mean, the empirical rule tells me that answer would be 68%. If I look at part B actually, it takes three standard deviations to make it all the way up to this 100.06. And if I go in the other direction, it also takes me 3 standard deviations to be down that low. So if I'm looking at 3 standard deviations, then that percentage is going to be 99.7%. And again, that's by the empirical rule. Okay, that takes us to the end of section 3.2. Be sure that you're keeping up with your homework on Canvas and MyStatLab. At the end of chapter 3, you'll have a quiz, and then we're going to stop and have a review day and be ready for our first test, which will cover chapters 1 through 3. Be sure you're attending the SI sessions and the Zoom sessions on Wednesday, or popping in for my office hours virtually if you need any help. And there is tutoring available, so if you are interested in that, reach out to me and we can see about getting you signed up for that. Thank you and have a good day.